AQA A Level Physics, nuclear radius. We're going to be doing this bit of the specification. So now we talked about this when we did electric fields. We've got an alpha particle with a certain amount of energy approaching a gold nucleus head on. And the question is, how close will it get? And we can actually work it out. And you need to be able to do this calculation, so learn this if you don't know it. So let's say that the alpha particle has 7 mega electron volts, for example, of kinetic energy. Now what's going to happen is that its kinetic energy will be transferred into electrical potential energy. So it will come screaming along and it will slow down and it will stop and then it will accelerate as it moves away. So as it approaches the nucleus, its kinetic energy is transferred into electrical potential energy. So my 7 mega electron volts, that's here. Here, the electrical potential energy is, if you like, it's little q times v. Q times v. Q is the charge on the alpha particle, which is 2e. V is the potential due to the nucleus, and you should remember that V is kq over r. K being 9 times 10 to the 9, or 1 over 4 pi epsilon naught, times q, the charge on the nucleus, which is 79e, because gold has an atomic number of 79, divided by r. And so this K79E over R is the potential due to the nucleus. And so now we can rearrange this equation, work out a value for R, 3.3 times 10 to the minus 14 meters. Now what does that tell us? Well, it's not the size, it's not the radius of the nucleus. What it is, it's called the distance of closest approach. And what it does tell us about the nucleus is that the nucleus must be smaller than that. And so the nuclei, the gold nucleus, is about 10 to the minus 14 meters, somewhere around there. There's another way that we can find out the radii of nuclei, and that's called electron scattering. You might get these muddled up. You remember there's electron diffraction we did in the first year, where you shine your electrons through at a graphite target. Now you can call this electron diffraction as well, or electron scattering, but don't get that muddled up with Rutherford scattering, because that's alpha particles. But anyway, before we talk about electrons, if you shine a laser through a small circular hole, so imagine I had a piece of card and there was a little circular hole in the card, and I shine a laser through there, then what I get is it's a 2-dimensional single slit diffraction pattern. And my 2-dimensional single slit diffraction pattern is a blob in the middle with rings around it. Okay, and the actual intensity against angle is this graph here. If we just look at 1/2 of the graph, intensity against angle, the important thing is that there is this minimum here. That's what we're going to use. That's the useful bit, is that minimum. And if we know the wavelength of the radiation of the light, in this case the laser, and if we measure the angle there for the minimum, then you can work out the radius of the hole. Yes, if we know lambda and we know theta min, yes, the angle for this minimum, then we can work out the radius of the hole, or the radius of the small ball. And that's useful because we can do it with electrons. When high energy electrons, and if you fire these electrons at atoms, we get a similar pattern. That's because it's the nuclei which are diffracting our electron waves. When we say high energy electrons, you're talking, look at the energies here, 360 MeVs, 420 MeVs. These are high energy electrons. They're not from your little standard electron gun. These are from some kind of particle accelerator. And we get a diffraction pattern, and we can now, the electrons are scattered by the nuclei. We can work out the wavelength of the electrons if we know their kinetic energy, and then we can work out their momentum. We're going to have to use a bit of relativity because they're so fast. Don't worry about that yet. And you can work out using the de Broglie equation, you can work out their wavelength. And from the angle of the first minimum, you can work out the radii of these nucleuses, of these nuclei. And here are some values here. So we have some isotopes of different elements, and we have the radius from these electron scattering experiments. And what we find is that if we plot radius against nucleon number, mass number, then we get a curve, which is interesting. If the mass number is bigger, then the radius is bigger. What's rather more interesting is if we do a graph of, now this is the radius cubed. So that is the radius cubed against the mass number. We get a straight line. Look at that. Okay. Now, if our nucleus is a sphere, what property is also proportional to r cubed? And you should really figure out it's the volume. So the volume of the nucleus is proportional to its mass number. That's not really surprising, is it? Yes, the more particles there are in the nucleus, the bigger its volume. It is actually interesting that the volume is proportional to the mass number. Okay, look at this. R cubed is proportional to equals a constant times the mass number. Now, the volume of a sphere is 4/3 pi r cubed. So that tells me that the volume of the nucleus is proportional to the number of particles in it. And that tells me that all nuclei have the same density. Like drops of water. If you imagine drops of water, there are little ones, there are bigger ones, there are quite big drops of water, but all of these drops of water have the same density. So if r cubed is proportional to a, then r is proportional to the cube root of a. And we say that r equals r naught a to the third. R is proportional to the cube root of a. What is r naught? Well, r naught is the value of r when a equals 1. In other words, it's the radius of a proton or a neutron. So this r naught is the radius of a proton. And if we plot this graph here, which is r against the cube root of a to the third, then the gradient will tell us the radius of a proton. And we get about a femtometer. Yeah, about 1.1 femtometers. That is the radius of a proton. Wow. So we know how big protons and neutrons are. We know how big nuclei are. Calculate the density of nuclear material. Okay, so 1U, that's the mass, about the mass of a proton, 1.67 times 10 to the minus 27 kilograms. You do it, work it out, do it for a couple of these. Do mass divided by volume. The mass would be the mass number times 1U, the volume 4/3 pi r cubed. Work out, pen paper calculator, couple of those, work out the density of nuclear material, and you get 321, that about 2.5 times 10 to the 17 kilograms per meter cubed. That's big. a comparison, you might have to do a comparison like this, okay? The Earth has a mass of 5.97 times 10 to the 24 kilograms. What would be the radius of a sphere made of nuclear material which had that mass? And it would be about 180 meters, okay? I've seen a similar question where you've got the sun, and the mass of the sun is ridiculously big, about 10 to the 30 kilograms. And if that shrank down to become a neutron star, its radius would be about, I believe, 27 kilometers, something like that. Nuclei are very, very, very dense. If you think about an atom, how much of the mass of an atom is in the nucleus, in this tiny nucleus? And it's 99 point lots of nines %.